Welcome back. Problem 14-11. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy in A36 structural steel W10 by 12 beam. Obtain the answer using the coordinate x1 and x4 and then x2 and x3. So you can see this is the beam W10 by 12. At this point there is a pin support. At this point we have a roller support, and at this end we have 6 skips load. Clear? The total length of the beam is 18 feet. Clear? So from the table mechanical property for A36 steel, E is 29 into 10 to the power 3 KSI, and from white flange section table, I moment of inertia for this is 53.8 inch power 4 for this beam. I will show you it later. So we have to determine the bending strain energy using x1 and x4 and x2 and x3. So let's start with the solution. So what will be the first step is that if you remove this pin support, so you'll be having reaction force. Let this is your point A and this is your point B. So the vertical reaction, and there will be horizontal reaction. Clear? So if you remove this roller support, so you'll be having reaction force that will be upward. Why upward? Because you can see 6 skips is downward, so this will be upward. Let this is RB, and this vertical reaction force at RA will be downward. So this is RAY, and this will be equal to RAX. So you will find this RAX, RAY, and RB by using the equation of equilibrium. So what will be the equation of equilibrium? So first equation of equilibrium is that sum of all movement about point A is equal to 0, and taking the counterclockwise movement as positive. So you can see this length is 12 feet. So in inch it will be 12 by 12 inch. Clear? That will be equal to 144 inch there, and this 6 feet will be equal to 6 multiplied by 12, which is equal to 72 inch. Okay, so sum of all movement about point A is equal to 0. So first movement will be this RB into perpendicular distance is this one, and this is producing counterclockwise movement, so it will be positive. So I will write RB multiplied by 12 multiplied by 12. Clear? The second moment is due to this 6 skips load, and the perpendicular distance is 18 feet. So I will write 18 multiplied by 12, that will be converted into inch, and this is producing clockwise movement, so it will be negative. So I will write minus 6 multiplied by 18 multiplied by 12 is equal to 0. So from here, this 12 multiplied by 12 times RB is equal to 6 into 18 multiplied by 12. Okay, so this 12 RB will be equal to 6 multiplied by 18. So from here, you will get RB is equal to 6 multiplied by 18 divided by 12, and you will get this RB will be equal to 9 kips. Clear? Okay. This will be RBY because this is the vertical component. Okay. So RBY is 9 kips. Now we'll find this RAX by using this equation of equilibrium. The sum of all forces along x direction must be equal to 0, and force toward right direction is positive. So there is only horizontal force RAX. There is no other force, so it means that RAX will be equal to 0. Now we'll find this RB by using equation of equilibrium. The sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So from here, RAY, which is equal to, which is not known, so RAY, which is minus. Clear? Okay. So RAY, which is minus, plus RBY, which is 9 kips, minus 6 is equal to 0. So it means that RAY is equal to 3 kips. Okay. Now you have all these reaction forces. So we will move toward finding bending strain energy. And we know that bending strain energy is equal to integral of m square dx over 2EI, and it is from 0 to length L. So what we are going to do is that first we will solve this by using x1 and x4 coordinate. So for x1 we will cut the beam over here, and we will draw the free body diagram. So for x1 coordinate, I cut the beam and draw the free body diagram. Here you can see you have RAY, which is 3 kips. Clear? This coordinate is having length x1, and when you cut it, you will be having a shear force V1, and there will be a bending moment M1. That this is your point 1. Now applying equation of equilibrium, that sum of all moment about point 1 is equal to 0, taking the counterclockwise moment as positive. So we will need this bending moment because we will use it in this equation. So 3 into perpendicular distance about point 1 is x1, and this is the moment which is positive. So 3x1 plus m1 is equal to 0. So from here we will get m1 is equal to minus 3x1. This is the moment equation for coordinate x1. Now what we will do is that we will do for coordinate x4, because in first part we have been given for x4. So x4 is this one. So we will cut the beam over here and take the right side in order to draw the free body diagram. So I will draw the free body diagram. It will be like this. You can see at this end we have 6 skip load. This is x4. Clear? So when you cut it, you will be having shear force upward. Here this is V4, and there will be a moment m4. Let this is point 4. So how we will find this m4? By using equation of equilibrium, that sum of all moment about point m4 is equal to 0 and taking the counterclockwise moment as positive. So this force 6 into x force is producing moment about point 4, that is clockwise, so it will be minus 6x4. So minus 6x4 plus minus this m4 is equal to 0. So from here you will get m4 is also equal to minus 6x4. Now you have both the moments. So what we are going to do, we will put it in this formula. So let's put it. So we know that strain energy due to bending moment is equal to, for coordinate x1, you can see its length from 0 to 144 inch. For x coordinate 1, x1 0 to 144 inch. Here, and for x4 it is from 0 to 72 inch. So we will put the value of m1. m1 is minus 3x1 square into dx divided by 2ei plus integral of from 0 to 72, and m4 is minus 6x4 whole square dx divided by 2ei. Now what you can do is that you can take 1 over 2ei common because they are constant. So we're left with integral of 0 to 144 minus 3x1 square dx plus integral of plus 1 over 2ei into integral of 0 to 72 minus 64x4 square into dx. Not minus 64, minus 6x4. Okay, so this will give us 1 over 2ei, and that we will get 9x1 square integral of 0 to 144 dx plus 1 over 2ei integral of 0 to 72 36x4 square into dx, and that we will get 9 over 2ei integral of x1 square will be equal to x1 cube over 3, and limit will be from 0 to 144. Similarly, 36 over 2ei and integral of x4 power square will be x cube 4 over 3, and integral from 0 to 72. So at the end, when you calculate it, and you can put the value 9 over 2ei into 144 cube over 3 plus 36 over 2ei into 72 cube over 3. Now you have the value of E and I. So 2 divided by E is 29 into 10 raised to power 3 ksi. I is given as from the table 53.8 multiplied by 144 cube over 3 plus 36 over 2 times 29 into 10 raised to power 3 divided by multiplied by 53.8 into 72 cube over 3. That will give you strain energy due to bending for coordinate x1 and x4. So when you solve this ui strain energy due to bending moment, that comes out to be 4.31 kips into inch, which is the answer of our first part. Now in part B, it has been asked to find the strain energy due to bending for coordinate x2 and x3. So for that, you can see x3 is here. So we will cut the beam over here, and we will take this as left side as a free body diagram, and to find the moment m3. So for that, I will draw the beam free body diagram of the beam. So you can see this is point A. So where you have the vertical reaction 3 kips downward. Clear? This is your point B. So where you have RBY, which is upward, and RBY is 9 kips. Clear? This total length is 144 inch, and this is the coordinate x3. So when you cut it, you will be having a shear force V3 downward, and you will be having a moment m3. That this is your point 3. So we'll find this moment by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point 3 is equal to 0, and taking the counterclockwise moment as positive. So about point 3, one moment is m3, which is counterclockwise. So I will write m3. The second moment is this 9 into perpendicular distance is 3, and this is also this is clockwise, so it will be negative. So minus 9 into x3, and the last moment is due to this 3 kips float, and perpendicular distance is 144 plus x3, and that will be clockwise, counterclockwise, so it will be positive. So I will write plus 3 into 144 plus x3 is equal to 0. So m3 minus 9x3 plus 3 into 144 will be 432 plus 3x3 is equal to 0. So m3 minus 6x3 plus 432 is equal to 0. So from here, this m3 will be equal to 6x3 minus 432. So this is the moment equation for coordinate x3. Now what we are going to do is that for coordinate x2, we will cut the beam over here, and we will draw the free body diagram of this right hand side to find the moment for coordinate x2. So for coordinate x2. So when you cut it over here and draw the free body diagram, so I will draw it like this. You can see this is 6 kip. There, this is point B where you have 9 kips load. The length, this is 72 inch here, and this length is x2, which is coordinate x2. So when you cut it, you will be having a shear force which is V2, and you will be having a moment m2. That this is your point 2. So we'll find this m2 by using equation of equilibrium. That is, sum of all moment about point 2 is equal to 0, and taking the counterclockwise moment as positive. So about this point 1 moment is m2, which is clockwise. So I will write minus m2. The second moment is due to this 9 kips load, and perpendicular distance is x2, and this is producing counterclockwise, so it will be positive, so plus 9x2. And the last moment is due to 6, and perpendicular distance is x2 plus 72, and this is producing clockwise moment, so it will be negative. So I will write minus 6 into x2 plus 72, and the sum of all moment about point 2 is equal to 0. So from here, m2 plus 9x2 minus 6x2 minus 432 is equal to 0. So minus m2 plus 3x2 minus 432 is equal to 0. So m2 will be equal to 3x2 minus 432. This is the bending moment due to coordinate x2. Now you have this and this. So what we are going to do, you know that strain energy due to bending moment will be equal to, for coordinate x2. X2 you can see start from here 0 and till 144 inch. And similarly x3 start from 0 to 72 inch. So for x2 0 to 144, the equation was m square m2 square dx2 divided by 2ei plus integral of 0 to 72 m3 square into dx3 divided by 2ei. Now you can put the value. So I will put the value 0 to 144, and 2 is 3x2 minus 432 square into dx2 divided by 2ei plus integral of 0 to 72, and 3 was 6x3 minus 432 whole square dx3 divided by 2ei. Okay, so you can take 1 over 2ei common from both, so 1 over 2ei, and we will left with integral of 0 to 144 3x2 minus 432 whole square dx2 plus integral of 0 to 72 6x3 minus 432 whole square dx3. Now we will apply the square formula, so you will get integral of 0 to 144. So 3x2 whole square will be equal to 9x2 square. 9x2 square plus 432 square will give you 186624 minus 2 times 3x2 into 432 will give you minus 2592x2, and that will be dx2 here, plus integral of 0 to 72 6x3 will be 36x3 square plus 186624 will be the square of 432 minus 2 times 6x3 into 432 will give you minus 5184 x3, and it will be into dx3. Okay, so now this is very easy. You can just put the value, you can integrate it. Okay, so 1 over 2ei, this will give you 9x3 cube over 3 in limit from 0 to 144 plus 186624 x2, not 3, this is x2, and limit from 0 to 144 minus 2592 into x2 square, and limit from 0 to 144 x2 over 2, this will be 2, clear, plus 36x3 cube over 3, and limit will be from 0 to 72 plus 186624 x3, and limit will be 0 to 72 minus 5184 x3 square over 2, and limit will be 0 to 72. Okay, so now you can easily solve it. You can just put the value. So I will put 1 over 2e is 29 into 10 to the power 3 ksi. I is 53.8. You can check it over here. Here. And you can put all other values. 9 multiplied by 144 cube over 3 plus 186624 into 144. Clear. Plus minus 2592 into 144 square over 2 plus 36 into 72 cube over 3 plus 186624 multiplied by 72 minus 5184 into 72 square divided by 2. And when you solve all this, you will get strain energy due to bending moment of coordinate x2 and x3 comes out to be 4.31 kips into inch. So this is the amount of strain energy that will be stored due to bending moment for coordinate x2 and x3. And that was all about this problem 14-11. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-12 that is taken from chapter 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is, if P is 10 kip, determine the total strain energy stored in truss. Each member has a diameter of 2 inch and is made of A992 steel. So you can see this is truss clear, and there is a load of P which is given as 10 kips. The diameter of each member, which is DAB, BC, CD, and each diameter is 2 inch clear. And due to this load in truss, you have to find the total strain energy stored in that truss. And we know that truss carries only axial load. So strain energy UI due to axial loading will be equal to sum of F square or N square L divided by 2AE, where A is axial load that is carried by member, L is length, A is area, and E is modulus of elasticity. So based on, you can see this is a member AD, this is member CD, this is BC, this is AB, and this is DB. So this formula will become, if you expand it, it will become equal to FAB square into LAB divided by 2 area of AB into E plus FBC square into LBC divided by 2 times area BC into E plus FCD square into LCD divided by 2 ACD into E plus F square AD into LAD divided by 2 AD into E plus FBD square LBD divided by 2 times ABD into E. So what we are going to do is that we will find these forces in each member of the truss. The length is also given, some is given, and some we will find it, and we will find the area as well. So let's start with the solution. So what we will do is that we will apply method of joint, and we will take joint B first, and you can see that due to this load, this CD will be in tension, this AB will be in tension, and this BC will be also in tension because it will cause elongation in this length, and this will be like this. Clear? So you can see this as a result. This member will exert load on point B like this will exert load like this, and this will be like this. So we will draw the free body diagram. This is your point B, clear, where you have P load which is acting downward, and that P is equal to 10 kips. Clear? This member BC will exert load on point B or joint B like this will be equal to FBC. This member AB will exert force like this will be equal to FAB, and this BD will exert force in upward direction. So now we will apply equation of equilibrium in order to find these forces. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force toward right side is taken as positive. So FBC is in right direction, so FBC minus FAB will be equal to 0. So from here we can say that this FBC is equal to FAB. Clear? And this will be our equation number 1. Now what we are going to do is that we will take another joint, and that will be joint D. Now you can see this is joint D. So this member will exert, as it is elongating due to this load, so this member will exert force in this direction. Clear? And these two members will exert force in this direction at point D. So we will take this joint D. This is your joint. This is your point D, where you have this this will be FBD. Clear? This will be FBD. Okay. So this, at this point you will be having FAD, FAB, and this another component will be FCD. Now you can see this is making horizontally theta. This is also theta. So you can see this is theta, and this will be also theta. Clear? So we will find these forces by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force toward right direction is taken as positive. So this FAD will have two components. Horizontal component will be this one, which will be equal to FAD cos theta. And similarly, this FCD will have one component horizontally toward left side, and this will be equal to FCD cos theta. Clear? So, and there will be vertical component of this, and this vertical component will be this one, And similarly, the vertical component of FBD will be this one. So this component will be equal to FAD sine theta, and this component will be FCD sine theta. So you can apply equation of equilibrium. So you can see two forces horizontally acting. One is this one and another is this one. So I will write it FAD cos theta minus FCD cos theta is equal to 0. So FAD cos theta will be equal to FCD cos theta. Cos theta, cos theta will cancel, and we will get FAD is equal to FCD. Clear? Now we will apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see now three forces. One is this one, the second one is this one, and third one is this FBD. Their sum must be equal to 0. So I will write it FAD sine theta plus FCD sine theta minus FBD is equal to 0. So you can see FAD and is equal to FCD. So FAD sine of theta plus FCD is equal to FAD. So I will write it as FAD sine of theta minus FBD is equal to 0. So 2 times FAD sine theta is equal to FBD. Clear? And we will get FAD will be equal to FBD divided by 2 sine of theta. Now we will again go back to joint B and we will apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force is FABD, which is upward, and the second one is 10 kips downward. Their sum must be equal to 0. So FBD minus 10 is equal to 0. So from here you will get FBD will be equal to 10 kip. Okay, so what we will do is that we will put this value of FABD over here and the sine theta value as well. So if you take sine theta will be equal to perpendicular, and perpendicular is this 4. Clear? So 4 divided by the hypotenuse, and the hypotenuse is not known. So you can see this is 3, this is 4. So hypotenuse will be equal to 3 square plus 4 square under the root, and that will be equal to 5. Okay, that will be 5 feet. So 4 over 5. So now put this value over here. So FAD will be equal to FBD is 10. So 10 divided by 2 multiplied by sine of theta is 4 by 5. 4 divided by 5, and that will be equal to 50 divided by 8, which is equal to 6.25 kip. Okay, since FAD is equal to FCD, so what we get is that FAD is equal to FCD, and that is equal to 6.25 kip. Okay, so let's go back. This is FAD, this is FCD, and due to this load, these two members will be in compression. So I will write it over here, compression. And this FBD will be in tension. How? Let me show you. You can see due to this load, this member BD will be in tension. Okay. Now we have this FBC is equal to FB3. Okay. Now we will apply method of joint at joint C. So you can see here you will be having one load that will be one will be the reaction force, which will be Cy, and this will apply load in this direction, and this member will apply load in this direction. Because you can see due to this load, this will be in tension. As a result, this will exert force at point C in this direction, and this member will exert load in this direction. Clear? So we will draw the free body diagram at joint C. So I will write joint C. So that this is your joint C. Clear? Where you have vertical reaction of roller support Cy. The force exerted by BC will be this FBC. Clear? And you will be having FCD, which we have calculated, that is 6.25 kip. Clear? Okay. If you look at this angle is theta. Clear? So I will write here, this is the angle, horizontal angle is theta. Clear? And we will apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So one force, which is FBC, is in opposite direction. So I will write minus FBC plus it will have two components. One is vertical and another is horizontal. So this component will be equal to plus 6.25 cos of theta is equal to 0. And we know that cos of theta here is equal to base over hypotenuse. So base is 3 and hypotenuse is 5. So 3 by 5. So I will write 6.25 into 3 by 5 will be equal to FBC. And FBC, you can see that FBC is not known. So 6.25 multiplied by 3 by 5 will give you 3.75 kip. And that will be FBC. So I will write it FBC will be equal to 3.75 kip. Okay. Now we know that FBC is equal to FAB. So from here FAB will be also equal to 3.75 kips. And these two loads, both loads will be in tension. This FBC and this is FBC and this is FAB. They will be both in tension. So now we have all the values. We are going to find area since diameter is same. So diameter is equal to pi by 4 d square. All the diameters are same. You can see this is, let this will be equal to d. So area will be equal to pi by 4 d square, and that diameter is 2 inch. So pi by 4, 2 square will give you pi, and unit will be inch square. Clear? And length of all is known. Clear? So this AB length is 3 feet, this is 3 feet, this is 5 feet, this is 5 feet, and this is 4 feet. So you can easily now put the value in each in this table. We will need E, modulus of elasticity of A992. So for that, we will go to the property table of the book. You can see this is the property table, and A992, E is 29 into 10 to the power 3 KSI. So we will note down it as well. E is equal to 29 into 10 to the power 3 KSI. So what we are going to do, we will put the value in the formula UI due to axial load is equal to, this is the formula. Let me copy it so that we can easily put the value. Okay, we'll copy it and we will paste it over here. This was the formula. Clear? So what we are going to do, FAB. So FAB, we will look FAB. FAB is this one, 3.75. So we will take the 1 over 2 AE common. 2 AE common. There, and we will left FAB 3.75 square, and we will multiply it with 3.75 LAB, length of AB, which is 3 feet. So in inch, it will be 3 into 12. Clear? Plus, we have done with this FBC. FBC is 3.75, and length is also same, 3 into 12. Let me show you. FBC is 3 feet. Okay. Plus, this is square. FCD is, you can see this is 6.25. So 6.25 square multiplied by length of CD. CD is 5. This is hypotenuse 5. So 5 multiplied by 12. Why 12? We are converting feet into inch. Clear? Plus FAD. FAD is also 6.25. So 6.25 square multiplied by length will be also 5 multiplied by 12. Let me show you FAD. This is also 5. We will left only BD, which is 4. Plus BD. FBD. FBD is this one, 10 kips. So I will write 10 square multiplied by 4 multiplied by 12. Clear? And we will also write it as 1 over 2. Area is pi and E is 29 into 10 to the power 3. Multiply by all these values. I will copy it and I will paste it over here. Clear? Okay. Now, when you solve this, you will get strain energy due to axial loading will be equal to 0.0576 kip into inch. So this is the amount of energy that will be stored in this truss. So, but before that, we will check it whether it's fail or not. So you can see here from this, you can see the maximum load is 10 kips. All other values are less. This is less, this is less. So maximum value is 10 kips. So what we are going to do is that we have FBD is maximum. Clear? And that is 10 kips. So stress, maximum stress will be equal to force per unit area. So 10 kips divided by area is pi inch square. Clear? So that will give you 3.18 KSI. So this maximum stress should be less than yield strength of A992. And we will check yield strength of A992. So what we will do is that we will move toward same property table, and you can see that A992 will have yield strength of 50 KSI. Okay. I don't know why my pen is not working, but you can see in the row, this is 50 KSI. So I will write it 50 KSI. So you can see 3.18 KSI is less than 50 KSI. So it means that it will not fail. Clear? And the amount of energy stored by the truss is 0.0576 kip. And that was all about this problem 14-12. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching, and also don't forget to share my video in your circle and help me in growing my channel further. Welcome back. In this video, we are going to solve problem 14-13 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum force P and the corresponding maximum total strain energy that can be stored in truss without causing any of the members to have permanent deformation. Each member of truss has a diameter of 2 inch and is made of A36 steel. So you can see this is truss clear that is acted upon by a load P. So we will find this P load clear and the maximum total strain energy stored in this truss. Each member has a diameter of 2 inch. So you can see I have written all this and it is equal to 2 inch, which is D, and they are made of A36 steel. So let's start with the solution. So first step is that we will find the normal forces in this member, and this normal forces they can be obtained by using method of joint. So we will apply method of joint at various joint in order to find the axial forces. So let's take this first joint B. So you can see due to this load P, this will elongate clear and this will behave like this. So this member CD will be in tension. Similarly, member BD and CD will be also tension. So as a result, member BD will exert force in this direction over this point, and similarly member AB and CB will also exert force in this direction at this point B. So we will draw the free body diagram. So first joint B, I will write joint B. So let this is your point B, clear. So where you have P load which is acting downward, clear. The force that member BD will act at point B will be upward, so this will be FBD. Similarly, the force acted by AB over point B will be FEB, and the force that member BC will exert over point B will be FBC. Now applying equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see horizontally two force, one in this direction, another one in this direction. Their sum must be equal to 0. So minus FAB plus FBC is equal to 0. So it means that FAB is equal to FBC. Okay, so this is your equation number 1. Now we'll apply method of joint at joint D. But before that, we will also apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So FBD is upward, minus P is downward, their sum must be equal to 0. So FBD will be equal to P. And this is your equation number 2. Now moving toward joint D. So you can see this is joint D. At joint D, the force that exert this member BD exert will be in downward direction. Similarly, this member will exert force in this direction and this member will exert force in this direction at point D. Why? Because you can see P is downward, which is causing tension in this. As a result, this will go downward, causing this to compress, and this, according to Newton's third law, this will exert force in this direction. So we will draw the free body diagram of joint D. This is your point D, where one load, which is FBD, will be downward. This is FBD, clear. This is your force FAD, and another one is FCD. This is FCD, and you can see they both are making angle theta. So this will be angle theta. This will be also angle theta. Okay, now applying equation of equilibrium. So first equation of equilibrium is that sum of all force along x direction must be equal to 0 and force toward right side is taken as positive. So you can see it will have two components. One will be this one, another one will be vertical. So this component will be equal to FAD cos theta, and this component will be FAD sin theta. Similarly, it will have also two components, one along x and other along y. So this will be FCD cos theta, and this one will be FCD sin theta. How we'll find sin theta? So you can see this base is 3 and this height is 4. So by using Pythagoras theorem, 3 square plus 4 square under the root will give you AD length or CD length, and that will be 5 feet. So this will be 5 feet. This will be 5 feet. Now cos theta is equal to 3 over 5 because base over hypotenuse, and sin theta will be equal to 4 over 5. So we'll apply this equation of equilibrium, that sum of all forces along x direction. So you can see along x direction, this and this force are acting. So I will write FAD cos theta minus FCD cos theta is equal to 0. So what we will get is that FAD cos theta will be equal to FCD cos theta. Cos theta will be cancelled. So FAD is equal to FCD. And this will be our equation number 3. Now applying another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and force upward is taken as positive. So you can see two forces which are acting upward and one force which is acting downward is FBD. Their sum must be equal to 0. So minus FBD plus FAD sin theta plus FCD sin theta is equal to 0. And FAD is equal to FCD. So I will replace this FCD with FAD. Okay, is plus minus FBD. So FBD will be equal to 2 times FAD sine of theta, and 2 multiplied by FAD and sine theta is 4 over 5. So 4 over 5. So what you will get is that FBD will be equal to, sorry, we are interested to find out FAD. So FAD, because FBD is equal to P. So FAD will be equal to 5 multiplied by FBD divided by 4 into 2. Clear? So we will get FAD will be equal to 5 over 8 FBD. This 5 by 8 is equal to 0.625 and FBD is equal to P. So I will get FAD is equal to 0.625 P. And this is your equation number 4. And we'll apply a joint method of joint using point C. So you can see you'll be having reaction force due to roller support CY, and the force this member will exert at point C will be in this direction, and this member BC will exert force in this direction over point C. And we will draw the free body diagram. So joint C. So this is this is point is C. So vertical reaction is CY. Clear? Horizontal force by member BC will be FBC in this direction, and this member CD will exert force in this direction. This is FCD, which is making angle of theta. Clear? So we apply equation of equilibrium that sum of all forces along x direction must be equal to 0, and in this direction force is taken as positive. So you can see this will have two components. One is this along vertical, and this will be horizontal, and this component will be equal to FCD cos of theta. Clear? So I will write FBC negative plus FCD cos of theta is equal to 0. So FCD cos of theta is equal to FBC, and cos of theta is 3 over 5. So I will write FCD is into 3 over 5 is equal to FBC. Clear? So FCD, okay, you can see FED is equal to FCD. So I will also write FCD will be also equal to 0.625 times P. Clear? So you can just put the value over here. So FBC will be equal to 0.625 multiplied by 3 over 5, and that will give you 0.375 times P. This is FBC. Okay. Now you can see this member, due to this load, this will be in tension, this will be tension, this will be in tension. These members will be in compressions. Clear? So you should know about this. Let's proceed further, and we will find the area as well. So area is equal to pi by 4 d square, since d is same for all, so which is 2 inch. So pi by 4, 2 square will give you pi, and area will be pi, and unit will be square inch. Now we are given that it is made of A36 steel, and you can see the largest load in this member is P, which is FBD. Rest all the forces are multiple of P, which is less than 1. So maximum load will be taken by member BD. So I will write member BD is critical. Why it is critical? Since it is subjected to greatest normal force or largest normal force, and that normal force is P. Okay. And we know that yield strength, which is the maximum load, is equal to maximum load in member FBD, not CD, it is BD, divided by the area. So we will not need yield strength of that. For that, you will go to the property table, and you can see that A36 steel having yield strength in tension is 36 KSI. So note down this value, 36 KSI. So I will write 36 here is equal to PF. BD is equal to P, so P divided by A. So from here, this P will be equal to 36 multiplied by A and 36 multiplied by pi. So you will get P will be equal to 113.10 kip. Or you can see that in short, P is equal to 113 kip. So this is the largest load P that can be applied on truss. Here, now next we will find the strain energy due to axial loading. So for that, what I will do is that I will copy it, or I will copy all this, and we will move toward next page so that you can easily pick the value of every force. So I will copy it, paste, and then we will resize it. Let me resize it for you. Okay. Now we will find the strain energy. So how you will find strain energy? We know that strain energy due to axial loading is equal to sum of F square into L divided by 2AE. So for different member A, B, C, C, D, and this will be equal to strain energy axial. For member AB, it will be equal to FAB square length of AB divided by 2 times area is same and E is same, plus for member BC, it will be FBC square LBC divided by 2 AE, plus for CD, it is FCD square LCD divided by 2 AE, plus for member AD, it will be FAD square LAD divided by 2 AE, plus for member BD, it will be FBD square LBD divided by 2 AE. If you take AE common, so I will write strain energy due to axial loading will be equal to 1 over 2 times A is pi and E for A36 steel. So I will go to the property table and it is for A36 E is 29 into 10 to the power 3 KSI. So I will write it 29 into 10 to the power 3 KSI. And we will left with FAB. So FAB, you can just put FAB. Okay, so you can see P is this one. So FAB. Where is FAB? So you can see FAB is equal to FBC and FBC is 0.375. So 0.375 times PP is 113 kips and this will be equal to FAB will be equal to 42.41 kip. Similarly, FAD is equal to FCD. You can see this is, and FCD is 0.625. So when you multiply P, so when you multiply it, you will get it 70.69 kips. And the last one is FBD, which is equal to P, and that is 113 kip. Okay, so FAB is 42 kips. So 42.41 square, 42.141 square into length of AB. Length of AB is 4 feet. Let me check it. Length of AB is 3 feet. So 3 multiplied by 4, convert it into inch, plus FBC square. So it is also 42.41 into length. BC is also 3 feet. So 3 multiplied by 12, 3 feet, 3 into 12. Okay, this is also not 4. This is 3 into 12. Okay, let me check it. FAB is 3 feet, FBC is 3 feet. So 3 into 12. Plus FCD. So FCD is 70.69 square. FCD and AD, these are 5 feet. Clear? So 5 feet multiplied by 12 will convert it into inch. Plus FAD. FAD is also 70.69 square multiplied by 5 multiplied by 12. And the last one is FBD. So FBD is 113 square multiplied by FBD. BD is 4 feet. So 4 multiplied by 12. Clear? And when you solve this, you will get strain energy due to axial loading in this truss will come out to be 7.371 unit will be kips into inch. Or you can say strain energy due to axial loading that is stored in truss without a permanent deformation of any member will be 7.37 kips into inch. And that was all about this problem 14-13. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning and clearing their concept. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-15 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy stored in the simply supported beam subjected to uniformly distributed load. EI is constant. So you can see this is a simply supported beam having pin support at this point and a roller support at this point. And there is a uniformly distributed load over a length of L by 2 from this pin support. So we have been asked to determine the bending strain energy stored in the beam. So let's start with the solution. So as we know that bending strain energy is equal to integral of m square dx over 2EI, and that will be from 0 to length. Limit will be from 0 to L. Now what we will do is that you can see if this is a point A and this is point B, and if you remove this pin support at point A, so you will be having a reaction force which is equal to RA, and if you remove this support at point B, so you will be having a reaction force which will be equal to RB. So first we will find this RA and RB by using equation of equilibrium, and when this distributed load is converted into a point load, it will act at the middle, and this load will be equal to W into our length which it acts, and it is WL. It will be L by 2, and it will be acting at half of L by 2, which is equal to L by 4. So this is L by 4, and this will be also L by 4. Now you can apply equation of equilibrium. So what will be the first equation of equilibrium? The first equation of equilibrium will be sum of all moments about point A is equal to 0, taking the counterclockwise moment as positive. So about point A, first moment will be this load, which is WL by 2, and that will act perpendicular distance is L by 4, and this is producing clockwise moment, so it will be negative. So I will write minus W into L by 2, and perpendicular distance is L by 4. The second moment about point A is due to this RB load, and the perpendicular distance is L, and this is producing counterclockwise moment, so it will be positive. So I will write plus RB times L is equal to 0. So from here you will get this RB into L will be equal to WL square over 8, and this RB will be equal to WL by 8. So this is reaction force by the roller support on the beam. Now we'll find this RA by using equation of equilibrium, that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, the first moment will be this WL by 2, and perpendicular distance will be this one. So L by 2 plus L by 4 will give you 3L by 4. And this is producing counterclockwise moment, so it will be positive. So I will write W into L by 2, and perpendicular distance is 3 by 4 times L. The second moment is produced due to RA, and perpendicular distance is L, and this is producing clockwise moment, so it will be negative. So I will write minus RA into L is equal to 0. So from here you will get RA into L will be equal to WL square 3WL square over 8. So from here you will get RA will be equal to 3 times WL by 8. So this is the reaction offered by the spin support on this simply supported beam. Now what we will do is that we will find internal movement. So for that I will cut the beam over any length of L by 2, and we will take this distance is x1, and we will draw the free body diagram. So I will write internal moments for coordinate x1. So I will draw the free body diagram. So let this is the beam. Here you have RA, which is upward, and this RA is 3WL by 8. This distance is x1 here, and there is a uniformly distributed load acting for a length of x1. This is W. And when you cut it, you will be having a shear force V1, and you will be having a moment M1. That this is your point 1. Now what we will do is that if you convert this W into point load, so it will be W into the length over which it acts, which is x1, and that will be acting at a half of x1. So this will be x1 by 2, and this will be also x1 by 2. Now we'll find this moment by using equation of equilibrium. So what will be that equation? That sum of all force moments about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point, the first moment will be this W into x1, and perpendicular distance is x1 by 2, and this is producing counterclockwise moment, so it will be positive. So I will write W into x1, and perpendicular distance is x1 by 2. The second moment is due to this load, and perpendicular distance is x1, and this is producing clockwise moment, so it will be negative. So I will write minus 3WL by 8 into x1. And the last moment is, you can see, external moment M1, or reaction moment, which is counterclockwise, and that is positive. And the sum of all moment is equal to 0. So from here, this M1 will be equal to 3WL over 8 x1 minus WX1 square over 2. Clear? So this is the internal moment for coordinate x1. Now what we will do is that we will find internal moment for coordinate x2. And what will be x2? So if you cut the beam over here any length of x by L by 2, so let this will be x2, and if we draw the free body diagram, it will be like this. So you can see here, this is point B, where RB, and RB is WL by 8. Clear? And this is the distance which was x2 coordinate. Clear? So when you cut it, you will be having a shear force V2, and you will be having a moment in clockwise M2. So we'll find this M2 by using equation of equilibrium, that sum of all moments about, that this is point O is equal to 0, and taking the counterclockwise moment as positive. So about this point O, the first moment will be due to this load WL by 8, and perpendicular distance is x2, and this is producing counterclockwise moment, so it will be positive. So I will write WL by 8 into perpendicular distance is x2, plus there is external moment M2, which is clockwise, and the sum of these moments will be equal to 0. So M2 will be equal to WL x2 over 8. So this is the internal movement due to coordinate x2. Now we have both these movements, so we will use this formula in order to find the bending strain energy stored in this beam. Okay, so what we will do is that we know that bending strain energy, let me write it, bending strain energy, which is equal to Ui, is equal to integral of 0 to L m square dx divided by 2 EI. If we take EI as common from, because we have two coordinates, so 2 EI will be outside, and we will left with integral of m square dx1 over 2 ei, and the limit will be from 0 to L by 2 for x1, plus integral of 0 to L by 2, and moment will be m2 square dx2 over, okay, so 2 ei is already taken outside, so no need to repeat it, okay, and this will be m1. Now you can just put the value of m1 and m2, which we have. M1 is this one and m2 is this one, so you can just put it. Ui is equal to 1 over 2 times ei into integral of 0 to L by 2, and m1 is 3 wl over 8 x1 minus wx1 square over 2 whole square into dx1, plus integral of 0 to L by 2, and m2 is wl x2 over 8 whole square into dx2. Now if you apply the formula a minus b whole square, so it will be equal to 1 over 2 ei integral of 0 to L by 2. This will be equal to 9w square L square x1 square over 64, clear, plus w square x1 4 over 4 minus 2 times this multiplied by this will give you minus 3w square L over 8 x1 cube into dx1, plus this will give you integral of 0 to L by 2 w square L square x2 square over 64 dx2, clear. Now if you further expand it, it will be equal to 1 over 2 times e1, and that will be integral of 0 to L by 2 9w square. Okay, so you can just skip this step. You can directly take the integral of x1 square into dx1. So it will be equal to 9w square L square over 64 multiplied by x1 cube over 3, and limit will be from 0 to L by 2. Similarly, it will be equal to w square x1 power 5 divided by 4 multiplied 5 will be 20 minus 3, and the limit will be 0 to L by 2. Similarly, minus 3w square L over 8 into x1 power 4 over 4, and limit will be from 0 to L by 2. Plus this will be equal to w square L square x2 cube over 64 multiplied by 3, and limit will be again 0 to L by 2. Okay, if you simplify all this and put the limits, replace x1 with L by 2 here, similarly here, and x2 with L by 2. You can do it, it's very easy. So you will get 1 over 2 ei into, okay, so you will, if you all simplify it, so you will get the final value will be equal to 17 w square L5 over 15360 ei. So this is the amount of strain energy that is stored due to bending, or it is also known as bending strain energy. And that was all about this problem 14-515. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-16 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy in A992 steel beam due to the loading shown. Obtain the answer using the coordinate x1 and x4 and then x2 and x3. I is 53.4 inch power 4. So you can see this is the beam where the loading is shown from this point till this. We have 8 kips per feet. At this end, we have pin support, and at this point, we have a roller support. So you have to find the bending strain energy due to first x1 and x4 coordinate and then x2 and x3 coordinate. So let's start with the solution. Let this is your point B and this is your point A. So if you remove roller support at point B, so you will be having a reaction force which is equal to RB, and that will be upward because this load is downward. So it will be upward, and this force will be, if you remove this reaction support, so the reaction force at RA will be also downward. And let this is RA. So we'll first find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. First, we will convert this 8 kips per feet uniformly distributed load into point load. So it will be act at the middle. So this load will be 8 into the length, which is 5 feet. That will be 40 kips. Clear? And this will act at a distance of 5 by 2, which is 2.5 feet. Okay, 2.5 feet. Okay, this 5 feet is also equal to 5 into 12, which is equal to 60 inch, and this will be 10 into 12, which is 120 inch. Clear? So later we will convert them into inch. Now we will apply equation of equilibrium at point A. So first equation of equilibrium is that this load into perpendicular distance is 10 feet and this is producing counterclockwise movement, so it will be positive. So I will write RB multiply by 10. The second movement is due to this load, which is 40 kips, and perpendicular distance will be this 12.5 feet. And this is producing clockwise movement, so it will be negative. So I will write minus 8 multiplied by 5 into perpendicular distance is 12.5. Their sum must be equal to 0. So 10 RB is equal to 8 multiplied by 5 multiplied by 12.5. So from here you will get this RB will be equal to 50 kip. Now you have this RB, you can apply another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is downward, so minus RA plus RB, which is upward, and that is 50 kips, minus this distributed load when converted into point load is minus 40 is equal to 0. So from here we will get this reaction force by support will be equal to 10 kips. Okay. Now you have this reaction force, so we will go toward our first part to find the bending strain energy for coordinate x1 and x2. So what we know that this bending strain energy is equal to integral from 0 to L m square dx over 2EI. So we will find moment for coordinate x1 and then moment for coordinate x2. So for x1, I will write for x1 coordinate, we will cut the beam over here and draw the free body diagram. So it will be like this. This is beam, this is coordinate x1. Clear? Here at this end we have RA, which is downward, and that is 10 kips. Clear? So when you cut it, you will be having a shear force that will be downward, and you will be having a moment M. That this is point 1, and this will be reaction moment at point 1. So we'll find this M1 by using equation of equilibrium, that sum of all moments about point 1 is equal to 0 and taking the counterclockwise moment as positive. Remember that this x1 is taken as inch. Clear? Okay, so about point 1, the moment will be, first moment is reaction moment, which is counterclockwise, and that is M1. So I will write plus M1. The second moment about point 1 is this 10 kips into perpendicular distance x1, and this is producing counterclockwise moment, so it will be negative. It will be also positive. Okay, that will be also positive. So I will write plus 10 into x1 is equal to 0. So it means that M1 is equal to minus 10 x1, and the unit will be kips into inch. So this is the moment for coordinate x1. Now we'll find moment for coordinate, x4, because in first portion it is x4. So for coordinate x4. So x4 you can see is over here. So we will cut the beam over here and draw the free body diagram. So this is the beam. Here this is the coordinate x4. Here this is the uniformly distributed load, which is 8 kip per feet. So in inch it will be 8 divided by 12. Clear? Kips per inch. Clear? Okay, so this distributed load when converted into point load, so it will be equal to this 8 over 12 into distance, which is x4. x4 is in inch, so that will give you unit kips. That will give you kip. Clear? And that will act at a distance of x by 4 from either side. So I will write x4 over 4. x4 over 2. x4 by 2. Okay, and when you cut it, you will be having a shear force V4, and you will be having moment clockwise, that is M4. That is, this is point 4. So we'll apply equation of equilibrium, that sum of all moment about point 4 is equal to 0 and taking the counterclockwise moment as positive. So you can see that one moment is this, which is clockwise M4, so it will be minus M4. The second moment is due to this load, which is 8 by 12 into x4, and perpendicular distance is x by 2. And this is producing clockwise movement, so it will be negative. So I will write minus 8 by 12 x4 into x4 over 2. The sum must be equal to 0. So I will get M4 will be equal to 1 over 3 x4, 1 over 3 x4 power 2. And that will be minus here. So this is the value of bending moment due to coordinate x4. You have both the bending moments due to coordinate x1 and x4. So we will get this strain energy due to bending will be equal to integral of first m1 square dx1 over 2EI, and for the limits for x1 will be from 0 to 120 inch. Clear? So I will write 0 to 120 inch. And for m4 square dx4 over 2EI, the limit will be from x4 you can see start from here and end over here, so 0 to 60 inch. So 0 to 60 inch. Now you can just put the value ui is equal to, we can take 1 over 2 e common because material is same and I is same. So you will get integral of 0 to 120 inch m1 square dx1 plus integral of 0 to 60 m4 square dx4. Okay. So put the value 1 over 2 ei into integral of 0 to 120 m1 is minus 10x1 square dx1 plus integral of 0 to 60 m4 is minus 1 over 3 x4 square whole square dx4. So ui will be equal to 1 over 2 times ei, and we will take integral 0 to 120, it will be 100 x1 square dx1 plus integral of 0 to 60 1 over 9 x4 power 4 dx4. Clear? So it will be equal to 1 over 2 times ei into 100. Integral of x1 will be x1 cube over 3, and limit will be from 0 to 120 plus 1 over 9, and integral of x power 4 will be x power 5 divided by 5, and limit from 0 to 60. Now you will take this, the value of E, from the property table. So you can go to the property table, and from here you can see E value for A992 steel is 29 into 10 to the power 3 KSI. So 29 into 10 to the power 3 KSI. I is also given, which is 53.4. So 53.4 multiply by 100 over 3 x1 cube. So from 0 to 120 plus 1 over 45 into x power 4 power 5, and limit from 0 to 60. Now when you solve this, you will get strain energy due to bending will come out to be 24 kips into inch. And if you want to convert it into kip into feet, so you will divide it by 12. So that will be equal to 2 kips into feet, which is the answer of our first part. Here, now we will move towards second part, and in second part we have been asked to find the bending strain energy due to coordinate x2 and x3. So let's move toward another page. So in this we will solve part 2. So for part 2 we will find the bending moment for coordinate x2. So x2 is here, so you can see you will cut the beam and take the right side portion. So let me draw the free body diagram of this. So this is point B. This was your point B, and from point B till this was coordinate x2. Here, this is x2, and total distance is this one, and the remaining this portion was given as 5 feet. 5 feet, that is equal to 60 inch. And from this point till this point we have uniformly distributed load of how much? 8 kips per feet. Okay. And when you cut it, you will be having a shear force V2, and you will be having moment M2. This is point 2. And what we will convert this uniformly distributed load into point load. So it will be in the mid. So 8 into 5 will be equal to 40, and unit will be kips. And that will act at a distance of 2.5 feet or 30 inch on either side. Okay. As we are dealing with inch, x is in inch, so we will find this m2. So how you will find? So sum of all moment about point 2 is equal to 0, and taking the counterclockwise moment as positive. So about point 2, one moment is this clockwise, which is m2, so it will be minus m2. Clear? The second moment will be due to this one load we have left is load at point B, which is RB. So RB was 50 kips. So 50 into perpendicular distance is x2, and this is producing counterclockwise moment, so it will be positive. So I will write plus 50 into x2. The third moment will be due to this load 40, and perpendicular distance will be now x2 plus 30, and this is producing clockwise moment, so it will be negative. So I will write minus 40 into 30 plus x2 will be equal to 0. So you can simplify it. M2 plus 50x2 minus 1200 minus 40x2 is equal to 0. So M2 will be equal to 10x2 minus 1200. So this is bending moment due to coordinate x2. Now we will solve for coordinate x3, and we will calculate the bending moment for the beam. So you can see this is the coordinate x3. So we will cut the beam and take the left side portion. Let me draw the free body diagram of the left side portion. So you can see this was your point A, where you have 10 kips load downward. Clear? This is your point B, where you have RB, which is acting upward, that is 50 kips. Clear? And this is the coordinate x3, where you cut it. X3 is in inch. So distance between A and B is 10 feet or 120 inch. X3 is in inch. Clear? And there is a distributed load over this portion, and this will be equal to 8 kips per feet. So if you want to convert it into inch, so 8 over 12 kip per inch. So when I convert it into a point load, so this will be 8 over 12 into perpendicular into distance, which is x3, and that will act at a distance of x3 over 2, x3 over 2. So this is your 0.3. So now when you cut it, so you'll be having a shear force V, and you will be having a moment M3. So we will find this M3 by using equation of equilibrium, that is sum of all moment about 0.3 is equal to 0, and taking the counterclockwise moment as positive. So about 0.3, the first moment is M3, which is counterclockwise, so it will be plus. So M3, the second moment will be due to this force, and perpendicular distance is x3 over 2, and this is producing counterclockwise moment, so it will be positive. So I will write 8x3 over 12 into perpendicular distance is x3 over 2. The another moment is due to this 50 kip load, and perpendicular distance is x3, and this is clockwise, so it will be negative. So I will write minus 50 into x3. And the last moment, which is produced by this 10 kips load, and perpendicular distance is 120 plus x3 inch, and this is also producing counterclockwise moment, so it will be positive. So plus 120 into plus 10 into 120 plus x3, their sum must be equal to 0. So M3 plus 1 over 3 x3 square minus 50 x3 plus 1200 plus 10 x3 is equal to 0. So from here M3 will be equal to 40 x3 minus 1 over 3 x3 square minus 1200, and the unit will be kips into inch. Okay. Now we have both M2 and M3. M2 is due to coordinate x1, and M3 is due to coordinate x3. So you can just put it in this formula. Strain energy due to bending is equal to integral of 0 to L m dx m square dx over 2 EI. So for coordinate x2, it will be 0 to x2 start from here, 0 to 120 inch, and I will write m2 square dx2 divided by 2 EI. And for coordinate x3, it will be x3 start from here and end here, so 60 inch, 0 to 60, and it will be m3 square dx3 over 2 EI. Clear? Now we can take 1 over 2 E common from both sides, so 1 over 2 EI, and we will left with integral of 0 to 120 m2 square dx2 plus integral of 0 to 60 m3 square dx3. Okay, just put the value 1 over 2 EI, and we will put integral 0 to 120 m2 is this equation, which is 10x2 minus 1200 dx2 square plus integral of 0 to 60 m3 is 40x3 minus 1 over 3 x3 square minus 1200 into dx3. Okay. Now you can see that you have two things. One is this one, and another is this one. Either you expand them, and we will use a shorter method. So remember these equations. First we will solve this by using calculator, and then this. So remember this equation 40x3, this one, and we will write it on calculator. So let me write it like integral of 40x minus 1 over 3, 0.33 x square minus 1200 and its square, and limit was from 0 to 60. And when you solve this, you will get 17224,128. And if you divide it with 10 to the power 6, so that will be 17.22 into 10 to the power 6. So I will write 17.22 into 10 to the power 6. Now we will solve this 2. So we will write this equation 10x2 minus 1200. So integral of 10x square minus 1200 whole square, and limit was from 0 to 120. And you click it, so you can see this is I think something is wrong. 10x square minus 1200, 10x2. Okay, it's not square, so this is not square, this is not square, so only 10x. Okay, now we solve this. So you can see 57,600 000 divided by 10 to the power 6 will be 57.6 into 10 to the power 6. So 57.6 into 10 to the power 6 multiply by 1 over 2 EI. So 2 is there, E is 29 into 10 to the power 3 KSI from the property table, and I is 53.4. 53.4. 53.4 will give you UI, strain energy due to bending, for coordinate x2 and x3. So when you calculate it, you will get strain energy due to bending will be 24 kips into inch. And if you want to convert it into feet, so you have to divide it by 12, so it will give you 2 kips into feet. So this is the strain energy due to bending for coordinate for x2 and x3. And that was all about this problem 14-16. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning as well. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-17 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the bending strain energy stored in the simply supported beam subjected to triangular distributed load. EI is constant. So you can see this is a simply supported beam having a triangular loading. Clear? The length of this total length of beam is L by L and the half length will be L by 2. At this point, we have pin support and at this point, we have a roller support. So you have, due to this loading, you have to determine the bending strain energy stored in this beam. So let's start with the solution. Let this is your point A and this is your point B. So if you remove pin support at point A, so you'll be having a vertical reaction force that this will be equal to RAY and you will be having a horizontal force which will be RAX. Similarly, if you remove this roller support at point B, so you will be having only vertical reaction force and this will be equal to RBY. So we'll find this RAX, RAY and RBY by using equation of equilibrium. Now you can see you have distributed load of W naught. So this W naught when converted into point load, so this will be equal to, as this is triangular load, so it will be 1 over 2 W naught and over the length which it acts is L by 2. Same is the case on this side, so you will convert this distributed load into point load, so it will be 1 over 2 W naught into L by 2. Clear? And that will act at a distance of L over 3 from this side. So L here is L by 2, so L by 2 over 3 is L by 6. So this distance is L by 6 and this remaining distance is 2 over 3 L over 2, so it will be equal to 2 L by 6. Same is the case over here. So this will be L by 6. Here it will be L by 6 and this distance will be 2L by 6. Okay. And distance from this point till this point will be equal to L by 2 plus L by 6, which will give you L by 2 plus L by 2 plus L by 6 will give you 2 over 3 times L. Now you can apply equation of equilibrium. So which equation of equilibrium we are applying? That sum of all moment about point B is equal to 0, taking the counterclockwise moment as positive. So about point B, the first moment will be due to this RAY and perpendicular distance is L, and this is producing clockwise moment, so it will be negative. So I will write minus RAY into perpendicular distance L. The second moment is due to this load and perpendicular distance is 2L over 3 and this is producing counterclockwise moment, so it will be positive. So I will write it plus W naught L over 4 into perpendicular distance is 2 over 3 times L. And the last moment that is produced due to this load and perpendicular distance is 2L over 6 and this is producing counterclockwise moment, so it will be also positive. So I will write W naught L over 4 into perpendicular distance is 2L over 6. That is equal to 0. So from here you will get RAY times L will be equal to W naught L square over 6 plus W naught L square over 12. There. And if you take LCM, that will be 72. 72 divided by 12 is 6. 72 divided by 6 is 12. And 12 multiplied by W naught L square will be this one. Plus 72 divided by 12 is 6. So it will be 6 W naught L square. That will be equal to RAY times L. Okay, so from here we will get 18 by 72 W naught L square and that will be equal to RAY times L. So RAY will be equal to W naught L over 4. Okay, so this is vertical reaction force AY. Now we can find RAX by using sum of all force along x direction must be equal to 0 and force toward right side is positive. So only one force RAX is acting, there is no other force, so it means that RAX is 0. Now we'll find RBY by using third equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RAY, which is acting upward, that is W naught L over 4 minus this force, so minus W naught L by 4 minus W naught L over 4 plus RBY is equal to 0. So from here, this RBY is equal to W naught L over 4. Now we have this reaction forces, so we will move toward finding the bending strain energy stored in this beam. So as we know that strain energy due to bending is equal to integral of m square dx over 2EI and the limit from 0 to L. So we'll find the internal moment by cutting this beam at any distance of x. So we will cut the beam over a distance of x and draw the free body diagram over here. So you can see at this point we have RA, which is equal to W naught L over 4. This total distance where we cut the beam is x, clear, and there is a triangular load of magnitude which we will find this. When you cut it, you will be having a shear force and you will be having a moment, and that this is 0.0. So you can see that here, if you take this larger triangle here, so their magnitude is W naught. So what will be the magnitude at this point over distance of x? So by using similar triangle, if we take W naught over L by 2 is equal to W over x. So this W will become equal to W naught x over L, and it will be 2 W naught x over L. So this W will be equal to 2 W naught x over L. Now when you convert this triangular load into point load, so it will be equal to 1 over 2 this load, which is 2 W naught x over L, and the length over which that is equal to x. Yeah, and this will acting at length of x by 3 from this point O. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0, and taking the counterclockwise moment as positive. About point O, one moment is this external moment, reaction moment, which is counterclockwise, so it will be positive, so I will write plus m. The second moment will be due to this load, and perpendicular distance is x by 3. It is also producing counterclockwise moment, so it will be positive, so I will write plus 1 over 2 W naught x square over L into perpendicular distance is x by 3. And the third moment is due to this W naught L over 4, and perpendicular distance is x, as it is producing clockwise moment, so it will be W naught L over 4 into x is equal to 0. Clear? Now what we will do is that we will simplify this, and when you simplify this, m plus this will be 2 will cancel, so it will be W naught x cube over 3L, clear, minus W naught Lx over 4 is equal to 0. If you further simplify it, so m will be equal to W naught Lx over 4 minus W naught x cube over 3L. And if you take W naught over 12L common, so this term, first term will become equal to 3L square x, clear? And the second term will become equal to minus 4x cube. Again, you can multiply this with this, so you will get this term, clear? And if you multiply this with this term, so you will get this term. You can check it as well. So it will be this one. So your moment equation, final moment equation will be W naught or 12L into 3L square x minus 4x cube. You can also use this equation as well, but this will be simplified. This is equation number 1. Now we'll apply for the bending strain energy. So bending strain energy. So bending strain energy, UI will be equal to UI bending will be equal to, you can see we have two portion, one is for this, another one is for this. So what I will write 2 times integral of 0 to L by 2, each segment is L by 2 into m square. M square is this one, so I will write W naught over 12L multiplied by 3L square x minus 4x cube whole square into dx divided by 2EI. So 2 will cancel with this, so we will left with 1 over EI integral of 0 to L by 2, and that will give you W naught square over 144 L square into 3L square x minus 4x3 whole square into dx. So take out these terms, so it will be W naught square over 144 EI L square, and we will left with integral of 0 to L by 2. So this will be equal to 9 L square x square plus 16 x 6, clear, minus 2 times this term into this term will give you minus 24 L square x4 into dx will give you UI due to bending. Okay, so UI due to bending will become equal to W naught square over 144 EI L square, and first term integral will give you 9L square x cube over 3 limit from 0 to L by 2 plus 16 x power 7 divided by 7 and limit from 0 to L by 2, and minus 24 L square x5 divided by 5 and limit will be from 0 to L by 2. Okay, now if you further simplify it and put this x is L by 2 in each portion, so let me put it also W naught square over 144 EI into 3L square, and it will be L cube over 8 minus plus 16 into L7, 16 by 7 into L7 over 7 power 7. No. 16, let me correct it as well. This will be also, this will be 3L square, L will be replaced with L by 2, which is L cube over 8 plus 16 over 7 into L7 over 2 power 7 minus 24 L square over 5 and L5 over 2 power 5. And again, when you simplify all this here, so you will get the final value will come out to be 17 W naught square L5 over 10080 EI. So final answer will be strain energy due to bending will be equal to 17 W naught square L5 over 10080 EI, which will be our answer. And that was all about this problem 14-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning too. Thank you for watching and supporting me.